Thank you for the introduction. So, like John said, I'm Arno, and I'm here today to talk to you about robust optimization of a gear model while coasting, using both Optimus and Romax. Here's what we're going to do. First, I'm going to describe to you the problem, then we're going to show what the optimization can do. And once we have done some optimization on this model, we'll see, is that robust, is that reliable, and then we'll have some conclusions. The problem that we're going to do is designing a gearbox, and it can contain thousands of variables. And a Romax designer wants to change a lot of those, and we can make it available as parameter. And so just inside of Romax, if you create a batch, you can select all the parameters that you want and dump that into a separate file. So just in the interface, select everything that you want to, all the parameters you want to play with, and export it. And you can decide what simulation you want to run, what are the outputs, what are the different load cases, and you can get all those results for the different load case and so on. And you can let Optimus worry about changing the values to find the best combination. The idea is really to automate this process and to be able to optimize it. The workflows in Optimus, it can be as simple as this workflow. So if you see here, we have on the left we have the input, on the right we have the output. We have Romax in the middle that's gonna modify those values and run the simulation, and Optimus will choose those values for you. And later on in this presentation, I'll show you a video on how quickly this can be done in Optimus. It's really a matter of minutes. You can also have very complex workflow. You see this one is used in aerodynamics, and you have some design parameter, you have a CAD tool, you have some aerodynamic computation, some mechanical computation, some post-processing including different software. It can be part of a bigger picture. So Romax Designer can be one piece of the workflow with a lot of different tools around. Like I said, it can be CAD, it can be FEA, it can be all those different kinds of things. And this workflow can be automated, it's multi-code, it can be multi-CPU, so Optimus will take care of distributing the jobs if you want to do some CFD on a cluster and Romax on your local machine, and maybe parallelize it using your different cores on your machine. That's all being able to be handled by Optimus. We can also control some logic. If some condition is satisfied, launch the meshing. If not, don't do it. All those kind of things can be included. And it needs to be repeatable. You need to be able to do this multiple times. If you run one problem once and you do the exact same a month later, you should have the same result. And so that's what we intend with repeatable. Here's one real case application that was done at Meritor in May 2016. They have this workflow. They have the Romax input that they're using, so they are changing some inputs in the Romax, and then they're grabbing the result from Romax, they're grabbing it, and they're using that inside of Ansys to be able to use that as an input for their Ansys simulation. And so automatically, whenever Romax is done, it's going to feed that to Ansys, and Ansys will update its computation. So you see here we have the load that's coming from Romax, and then we'll have some geometrical input coming from the CAD that will go into Ansys, and here you have the FEA analysis using the load that it got from Romax and seeing what the geometry needs to be. So you can optimize your geometry also based on the load that you're getting from Romax. That's one example of something that can be done. Something else that can be done is that you can grab some, for example, if you have a housing, you're going to have a stiffness matrix. You can convert that from Romax to Ansys, from Ansys to Romax, to be able to check what the parameters are going to be, sharing this stiffness matrix between those two different software. So that's something else that can be done in this case between Ansys and Romax. But we use Ansys in this example, but it can be any other FEA tools out there. And here also the geometry input is also directly feeding into Ansys, but it could very well go through one CAD tool such as ProE, NX, SolidWorks, all of those. So let's go back to our example. We'll do a macro geometry analysis of a gear, and we have input parameters. We're going to look at the pinion of the gear set, and we're going to have the right and the left flank. We'll look at the involute barreling, the involute slope, the lead crown, the linear tip relief. For the right flank, we have the lead slope, and the left flank will be equal as to the right flank lead slope. So that's going to be one parameter for both sides. We'll use the same. All the others we're going to have two parameters. And you see here we are also giving the range that we are giving. So Optimus will be able to play with those parameters within those range, which is between 0 and 40 micrometer, for example, for the involute barreling on both flanks. We're going to have different load cases. We're going to do coasting at 20%, 60%, and 100%. And we're going to do a driving 20, 40, 60, 80, and 100%. So those are all the load cases that we'll analyze. And for all those load cases, we're going to look at specific outputs. We're going to look at the tip load ratio, the root load ratio, the left and the right edge load ratio. And they all need to stay below 85%. Those are our constraints. We cannot go above 85%. And what we're going to try to do, our goal, is to minimize the transmission error and the peak surface load. So those are the two outputs that we'll try to minimize. And we'll do this for each of the load cases. So those constraints, remember we had 8 load cases. We have 4 constraints, so that's 36 constraints total. And we're going to have 2 outputs that we try to minimize per load case, so it's going to be 16. Here, let's take a look at how it's built in Optimus. So here, you see we have Romax input, output, and action. And we link all those 3 together. And now grabbing here our XML, so that's the file that was generated by Romax, and here we'll have a list of all the available inputs. And in this case, I'm actually going to grab all of them and add them to my workflow. Click on OK. That's the only thing you need to do to grab those inputs. On the output side, it's going to be the same thing. I'm going to grab the same XML file. It's going to contain all my load case. And for example, grab all my left load ratio or all my peak loads. I'll extract all of those in my Optimus. You see we have different filter to go different cases for each load case, each type and per unit. So those are different filters that we can use. So we'll extract all of those. Here I'm just selecting all of them, and just like that we're done. We've defined our input, we've defined our output, and inside of the Romax solver I'm going to just say, oh, this is my input, this is my output, and then we're done. Optimus knows what are the files. And here we're not going to do anything parallel. We're just going to run this as what we call a server mode, which means that Romax is not going to close every time. Romax is going to stay open. The only thing it's going to do is load the model and the different values of the model. And so this can be very quick. You don't have to open and close Romax every time, so you're gaining a lot of time. But that also includes, if you do so, if you don't open and close Romax every time, it also includes, well, it means that you cannot use the parallel. And if you have different machine to run, you can, for example, submit different Romax computation if you have multiple Romax license available. For example, during the weekend or at night, you'll be able to take advantage of those extra license, especially if the Romax run are getting longer. And what we'll do is that we'll do a multi-objective optimization, which means we're going to try to minimize 2 different things at the same time. We want to minimize the transmission error, and we want to minimize the peak surface load. And in just a moment, I'll explain what you mean with the normalized sum for the transmission error and the peak surface loads. And the constraint that we'll have is that all the ratio needs to stay below 85%. And remember, if we had 8 load cases, we have 4 ratio per load case, so that means 36 constraints that we'll need to check for all our input values that we are going to check. And so we'll do multi-objective optimization, which means we'll try to minimize those two at the same time while satisfying all the constraints. The normalized sum, what we mean with this is that we'll take this as a measure for comparing results. To compare one gearbox to another, we'll take the default case, so the non-optimized case that we have, and we'll say, okay, we'll do a sum of all our transmission error, for example, and divide it by the value of the default load case. So it means no improvement means we'll have a value of 1. The value of 0.8 will mean an average of 20% improvement over all the load case, on average. So the optimization strategy, it will compute the model in Romax Designer and takes about 1 minute per run. We can parallelize on different cores or on different machines to take advantage of the additional licenses, especially during nights and weekends where you're not using those Romax licenses. Since here it goes very quick to solve the model, we'll do a direct optimization on the model, and we'll use an evolutionary based method. So we won't be building any response surface method for now. I will show you in a minute what we mean with response surface model approximation. It's basically computing trend lines. So the algorithm that we are using is a genetic algorithm, and it's based on nature. So we are mimicking the behavior of, in this case, fishes, and how they behave when they are together. And it's an algorithm called particle swarm algorithm, and it's very efficient, especially in multi-objective optimization case. With multi-objective, we mean we want to minimize goal 1 and minimize goal 2. And usually, when you do so, goal 1 and goal 2 are going to be opposite. So when you're going to try to minimize goal 1, goal 2 is going to go up. And when you're going to try to minimize goal 2, goal 1 is going to go up. So what we'll get as an output is all the optimal compromises. So this is what we call a Pareto front, and you see it's in red on the graph here, the red points on the graph, which are all the optimal points, and all the yellow we can do better both in goal or in goal 1 or in goal 2, or do at least better in one and the same in the other. So the reds are all the optimal compromise, which means we cannot do better in terms of goal 1 without doing worse in goal 2 and vice versa. Here you see we have the particle swarm optimization result, and you see actually how the algorithm is behaving. And you see all those points at the beginning, they are moving more and more towards the bottom left. And that's all the computation that have been done in Romax. And we see here we have the Pareto front, which is located in that region. You have the direction of improvement. All the blue points are points that are satisfying all the constraints, so below 85% for all the ratio, and the orange points are points that violate at least one of the constraints. On this Pareto frontier, we'll grab one of the points, and you see here if we grab this specific point, and we see here the normalized peak load and the normalized harmony, the transmission error, and we here are going to see the value of our input. So that's what we need to put in terms of tip relief, involute barreling, involute slope, lead crown, and lead slope to get those values on the output side. That will give us a 24% improvement in terms of transmission error, and it will give us a 44% improvement in terms of normalized peak surface load. And all our constraints are satisfying the constraint at 85%. It took about 450 runs, so we did about 450 designs to get to this value. So it ran for about 7 hours. It was less than one night on one machine. I launched it before going home. The next morning when I come, all the results are waiting for me, and I have my optimum solutions. Now what we want to check is that optimum robust, which means if we change a little bit the value on the input side, if my invalid slope is not exactly what I ask, what is the consequence on my output? So we have to take into account some uncertainty, because when you're going to build your gearbox, you're going to have some of those flaws in the design, either directly or after a while. If it gets a bit damaged or so. So we'll take the uncertainty into account, and we'll add a sigma. We'll take a normal distribution with a certain sigma on our involute bearing, involute slope, lead crown, linear tip relief, and lead slope. So this is the value that we are going to take for the sigma. So 0.4 micrometer. And we're going to run a Monte Carlo simulation. If you run a Monte Carlo simulation with 100 points distributed around the optimal solution, we'll see that 2 of those 36 constraints will be violated. It's at drive 100%, the right edge load ratio, which gives you a probability of failure of 45%. So we have 45% chance to be above 85%. And on the coast at 100%, we have the root load ratio that's also failing from time to time, and we see the probability of failure there is 13%. Now we're going to try to find a design that is not failing for the drive 100% and the coast 100%. We'll go back to Optimus and say, all right, now the constraint is not going to be 85% for all those ratios. It's going to be 85%, but we want to be sure, even if you have some difference in the input, we want to be sure that those constraints won't be violated. And we want all those points here to be blue. We don't want any orange, which means we are above 85%. And when we look for those, we can look at the different factors on the input and the output side. So we have what we call correlation values. And correlation values are going to be 1 or -1 if you have a big correlation between an input and an output, and going to be very close to 0. It's going to be blue in this graph, very close to 0 if you have almost no correlation. You see, for example, involute barreling has a 100% correlation with itself, which makes sense, and almost no correlation with the other inputs, because of course those inputs don't depend on this value. We are doing this independently of all those inputs are chosen independently. And we see, for example, that this, if we look at our 2 constraints, the involute barreling has a big effect on the coast 100% for this ratio, the involute slope also, but almost none on the drive at 100%. And the lead crown, the lead slope have a huge impact on the drive 100% on this ratio, and almost none on the coast 100%. And the tip relief has almost no impact on those 2 constraints. And so this already gives us an idea that about which input has what influence on what output, and this is going to help the designer into knowing what is going to help us to do so and to get a robust design. So it's very demanding to do a robust analysis. It means it can require a lot of points. Imagine if you have to run what we call a Monte Carlo analysis, which is going to be random points around the value you chose, and you have to do this for 400 times for your optimization. This can take a lot of computation. So what we'll do is that we'll build what we call a response surface method, or a meta model. A meta model in Excel, you've all remembered this, when you have a cloud of points, you can fit a curve through it. And that's what we call a trend line in Excel. And so that's the idea behind a response surface. Except in Optimus, you are doing this in many dimensions. You have a lot more input than just these seconds that you have here in this example. You have many inputs, and we'll build such a response surface for all the outputs. And of course, we're going to do something that are better than just a linear or a quadratic model. We can have some interpolation model that are actually going to fit through every point. You have neural network. You have all those different kind of response surfaces that are available inside of Optimus. And we'll use that to do our robustness. So if you do a Monte Carlo, which is very expensive, you can do that on the response surface, then you're good. Another way to do is to use the first order second moment method, which is a specific method that is used in Optimus to use the gradient to use a gradient at a certain point to evaluate the robustness of this point. And that's what we are going to use. And so, like we said, we have an optimization that takes about 400 or 500 experiments. So those are all the points that the Optimus is trying. So he's trying, what about this one? What about this one? What about this one? He's doing this in a smart way, of course, but it's still going to require points. And if we want to evaluate the distribution on the output side versus the distribution on the input side, so what is the impact of an input change on the outputs, we're going to have about 7 computations. So you have to launch your Romax simulation 7 times per experiment. So that gives us about 3,000 points that we're going to compute, and we'll do that on the response surface, like I said. And we'll find a new point. And so the new point that we're gonna grab, we'll do a multi-objective optimization again, and we'll see that now we have minus 18% and minus 22% in terms of transmission error and peak surface load. So those, we're still doing a lot better. 20% gain on average on the transmission error and the peak surface is very nice, especially now we are satisfying the constraint for all those ratios. So all those ratios are below 85%. And if you add some probability to have some wrong value during the design with a certain probability, which is about 0.4 micrometer for all of those inputs in terms of sigma, we get the probability of failure. So the failure means one of the constraints will be above 85%. So the probability of failure will be less than 5%. So that's usually what we call a 3 sigma analysis. And so now we have another solution which is more reliable. It's not as good as the one we had before, but at least we know that small changes in our inputs are not going to have a dramatic effect on our outputs. As you've seen in this presentation, the setup in Optimus is very quick. First, you need to go into Romax Designer and grab all the inputs that you would like to change on the input side and on the output side, which load case you want to run, and create and export a batch running format. Then the setup in Optimus, as you've seen in the video, takes less than 2 minutes to grab the inputs and grab the outputs. You then need to go and select which one are your constraints, which one are your objective, and set the ranges. But all in all, it takes less than half an hour to do so. To run the entire process, it took less than 1 night. To do this direct optimization inside of Romax, it took 7 hours, so you can launch it before you go home and come back the next day with the result. The improvement we could get with this direct optimization was about 25% in peak load and 45% in transmission error. And all the ratio were below 85%. So all the constraints were satisfied. So that's very good result. And then what we did next was look at the tolerances and check if some slight changes in the input could not have dramatic effect on the output. And we saw that some of those input value, when they were changing too much, were getting us failing design. We saw that, for example, that we had 45% in the drive 100% load case. For one of the ratio, it was about 45% of the time it was failing. And so we launched a robust optimization to take that into account, and we stayed below 5% in terms of robustness, which is a very big improvement. Of course, it meant we were only having 20% improvement in peak load and 20% in transmission error. So you have to have a trade-off between you really want to have something that's very efficient or something that's very robust. And that can also be depending on your manufacturing tolerances and the cost you have to have those tolerances to be very tight. And so that's using Romax, but we've seen that you can also link your Romax to different tools. It can be an Excel sheet, it can be an FEA tool, it can be some CAD tool, or those can be used in Optimus, and we can have Romax Designer as a brick in a much larger workflow. Thank you for your time. If you have any questions.